It was 1945, and a German-born mathematician named Neugebauer, working at Brown University in Providence, Rhode Island, opened a steel drawer in the Yale Babylonian collection and pulled out a clay disc roughly the size of a coaster. The disc had been sitting in that drawer, unexamined, for at least 3 decades. It had arrived at Yale around 1912, acquired by an agent of the banker J.P. Morgan from antiquities markets in southern Mesopotamia. It was catalogued as YBC 7289. Nobody had published it. Nobody had written about it. It was a piece of homework. Scratched into the surface of the disc was a square, with both diagonals drawn across it. Along one side of the square, a number in cuneiform, 30. Along the diagonal, another number, 1, 24, 51, 10, and below that, a third, 42, 25, 35. Neugebauer recognized what he was looking at immediately. The number along the diagonal, 1, 24, 51, 10, was written in base 60, the number system the Babylonians had been using since the 3rd millennium before the Common Era. Converted to decimal, it reads 1.41421296. The modern value of the square root of 2 is 1.41421356. The Babylonian value, pressed into a lump of clay by a student in southern Iraq sometime between 1800 and 1600 before the Common Era, is accurate to 6 decimal places. The error is less than 1 part in 2 million. That was 1,200 years before the birth of Pythagoras. Neugebauer published the tablet in 1945 with his colleague Abraham Sachs in a book called Mathematical Cuneiform Texts, issued by the American Oriental Society. Page 43. It is one sentence in a catalog of hundreds of tablets, and it changed the history of mathematics. The reason it matters is not just the number. It is what the number means. The square root of 2 is the length of the diagonal of a unit square. If you draw a square with a side of 1 and measure across the corner, the line you get is the square root of 2. The Babylonian student who made YBC 7289 was solving exactly this problem. He drew the square. He wrote the side. He looked up the constant in a reference table, multiplied it by 30, and wrote the answer. The reference table survives. It is another Yale tablet, catalogued as YBC7243. Line 10 of that tablet gives the value 1, 24, 51, 10, with an explicit label in Akkadian that translates to the diagonal of a square. This was not a one-time discovery. It was a standard number, taught in schools, looked up in tables, applied to problems. The Babylonian scribal curriculum treated the square root of 2 the way a modern engineering student treats pi. It was infrastructure. To understand those 3 cuneiform numbers, you need to understand the system they were written in. The Babylonians counted in base 60, not base 10. Every digit position represented a power of 60 rather than a power of 10. In this system, the number 1, 24, 51, 10 means 1 times 60 to the 0, plus 24 times 60 to the minus 1, plus 51 times 60 to the minus 2, plus 10 times 60 to the minus 3. Work it out, and you get 305,470 divided by 216,000. That is 1.41421296. The question that follows immediately is why 60? The answer is divisibility. 60 is the smallest number divisible by 1, 2, 3, 4, 5, and 6. It has 12 factors. 10 has 4. For merchants dividing grain, for surveyors splitting fields, for astronomers chopping the sky into degrees, 60 is enormously more flexible than 10. You can split 60 into halves, thirds, quarters, fifths, sixths, tenths, twelfths, 15ths, 20ths, and 30ths without ever producing a remainder. Try doing that with 10. This system is not ancient history. It is current infrastructure. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. These are Babylonian. They passed through Greek astronomy, through Hipparchus and Ptolemy, through Arabic mathematics, through medieval European universities, and into the clock on your phone. Every time you read a coordinate or check the time, you are using Sumerian arithmetic. The Babylonians also invented something else that deserves attention. They invented place value notation. The idea that the position of a digit determines its value, that a 3 in the hundreds column means something different from a 3 in the tens column, was a Babylonian innovation achieved no later than the 20th century before the Common Era. The Indians developed their own place value system independently roughly 2,000 years later. The Babylonians were first. They did not, however, invent zero. In the Old Babylonian period, an empty position was marked by a blank space, sometimes barely visible on the clay. A proper zero symbol appears in Babylonian astronomical texts only in the Seleucid period, around 300 before the Common Era, which is still 2 centuries before the Indian zero. The next question is how the Babylonians calculated the square root of 2 in the first place. The most probable method is what modern mathematicians call the Babylonian algorithm, though it was reinvented independently by Hero of Alexandria in the 1st century and by Isaac Newton in the 17th. The procedure is simple. Start with a guess. Call it A. Divide 2 by A. Average the result with A. Repeat. Each iteration roughly doubles the number of correct digits. Start with the equals 1. 2 divided by 1 is 2. The average of 1 and 2 is 1.5. That is the first iteration. 2 divided by 1.5 is 1.333. The average of 1.5 and 1.333 is 1.4166. That is the second iteration. 2 divided by 1.4166 is 1.4117. The average of 1.4166 and 1.4117 is 1.414256. That is the third iteration, and it is already accurate to 5 decimal places. By the fourth iteration, you have 10 correct digits. The algorithm converges so fast that a Babylonian scribe, starting from a rough guess of 1.5, could reach the value on YBC 7289 in 2 steps. The clearest cuneiform evidence for this method comes from a tablet now split between the British Museum and the Vorderasiatisches Museum in Berlin, catalogued as BM9 6957 plus VAT 6598. It is a problem text from Sipar containing 30 exercises on rectangles. Problem 18 walks the student through the procedure for finding the diagonal of a gate step by step, using the iterative averaging method in geometric form. David Fowler and Eleanor Robson published the definitive analysis in Historia Mathematica in 1998, under the title Square Root Approximations in Old Babylonian Mathematics, YBC 7289, in context. YBC 7289 is not alone. 100 miles south of New Haven, in the Rare Book and Manuscript Library at Columbia University in New York, there is a tablet catalogued as Plimpton 322. It is 12.7 centimeters wide, 8.8 centimeters tall, and 2 centimeters thick, broken along the left edge. George Arthur Plimpton, a New York publisher, bought it from the archaeologist and antiquities dealer Edgar J. Banks around 1922 for approximately $10. Banks said it came from Senkereh, the site of ancient Larsa in southern Iraq. Eleanor Robson of University College London dated the tablet to between 1822 and 1762 BCE, based on the script style and the administrative format of the table. The tablet contains 4 columns and 15 rows of numbers. The rightmost column is simply a row counter, 1 through 15. The other 3 columns contain, in every row, 2 of the 3 sides of a right triangle that satisfies the Pythagorean theorem: the short side and the diagonal. The long side, which would have occupied a now missing column on the broken left edge, can be calculated from the other 2. The triples are not small. Row 1 is 119, 120, 169. Row 4 is 12,709, 13,500, 18,541. These numbers cannot have been found by trial and error. The triple in row 4 is too specific, too large, too exact to be a lucky guess. Plimpton 322 is proof that the Babylonians of roughly 1800 BCE possessed a systematic algorithm for generating Pythagorean triples. That is 1,000 years before Pythagoras and 1,500 years before Euclid recorded the formula in the Elements. What Plimpton 322 means has been debated for 80 years. Neugebauer and Sachs in 1945 read it as pure number theory. Eleanor Robson in 2001 and 2002 argued it was a teacher's reference table for generating classroom exercises from reciprocal pairs, not a research document. Daniel Mansfield and Norman Wildberger of the University of New South Wales argued in 2017 that it is the world's oldest trigonometric table, using exact ratios rather than approximate angles. Robson pushed back, pointing out that the old Babylonians had no concept of a measured angle and no instrument for measuring one. The debate remains open. In 2021, Mansfield published a second finding. A tablet catalogued as C427, excavated in 1894 at Sipar and stored unexamined in the Istanbul Archaeological Museums for over a century, turned out to be a land survey. It records the legal subdivision of a marshy field, and the surveyor, a man named Sin Bel Apli, who was involved in a property dispute over date palms, used 3 Pythagorean triples to construct perpendicular boundary lines: 3, 4, 5, 8, 15, 17, 5, 12, 13. This is the oldest known example of applied geometry. A Babylonian surveyor, standing in a marsh in Iraq nearly 4,000 years ago, used the theorem that bears Pythagoras' name to settle a real estate argument. Pythagoras of Samos was born around 570 BCE and died around 495 BCE. He left no writings, not one sentence. Everything attributed to him comes from later sources. Xenophanes and Heraclitus describe him as a religious teacher and a wonder worker, not as a mathematician. The image of Pythagoras as the father of Greek geometry was built by Neoplatonic biographers writing 700 to 900 years after his death. Porphyry and Iamblichus, both writing in the 3rd and 4th centuries, are the principal sources, and both explicitly state that Pythagoras studied in Babylon with the Chaldeans after being captured by the army of Cambyses II in 525 BCE. Porphyry writes that it was from his stay among these foreigners that Pythagoras acquired the greater part of his wisdom. Whether or not Pythagoras personally traveled to Babylon is unprovable. What is provable is that the mathematical results the Greeks called theirs were Babylonian property 1,200 years earlier. The Pythagorean theorem, the systematic approximation of square roots, place value sexagesimal notation, Pythagorean triples, all attested on clay tablets from the time of Hammurabi. There is one more detail that makes the contrast between Babylon and Greece almost painful. When the Greeks discovered that the square root of 2 cannot be expressed as a ratio of whole numbers, that it is what we now call an irrational number, it caused a philosophical crisis. The Pythagorean Brotherhood believed that all of reality was built from whole number ratios. A number that could not be expressed as a ratio was, to them, a violation of cosmic order. The legend transmitted by Iamblichus says that a member of the Brotherhood named Hippasus of Metapontum was drowned at sea, either by the gods or by his own colleagues, for revealing the secret of irrational numbers to outsiders. The Babylonians had no such crisis. They calculated the square root of 2 to 6 decimal places, multiplied it by 30, wrote the answer on a clay disk, and moved on to the next problem. They did not ask whether the number was rational or irrational. They did not care. It was the diagonal of a square. You could draw it. You could measure it. You could compute it. That was enough. The reason the West credits Greece and not Mesopotamia for these results is not mathematical. It is historical. Cuneiform died as a living script around the 1st century of the Common Era. The last datable cuneiform tablet is an astronomical almanac from 75. For 1800 years after that, the clay tablets sat under sand in southern Iraq, unreadable. The script was not deciphered until 1857, when the Royal Asiatic Society in London tested 4 scholars with an unseen tablet, and all 4 produced near-identical translations. Cuneiform mathematics was not published until Neugebauer in the 1930s. The entire European mathematical tradition, from the medieval universities through the Enlightenment, was built on the assumption that mathematics began with the Greeks, because the Babylonian record was literally invisible. Why BC 7289 is still in a steel drawer at Yale. It is still the size of a coaster. The square is still drawn on it, the diagonals still crossing, the number 1, 24, 51, 10 still legible in cuneiform along the diagonal. It has been there for over a century. It was homework, and it is 1,200 years older than the man whose name is on the theorem.